So finally, we'll take a look at a cost-benefit analysis of doing feeder automation. And when we add the automation to the circuit as far as utility costs, we got to consider the capital investment. I think that's kind of obvious. Some other things that you would include in there could be additional manpower costs. And so this is going to add to your operational expenses during the year. We're just going to go ahead and neglect that in this particular example. And there could be other sort of costs in there too, to maintain the system. But let's just go ahead and just keep it kind of simple. We're just going to focus on installed cost. The benefits of automation would obviously be the lower SAIDI and SAIFI indices, but we got to put a dollar number on that as well. And we'll do that at the toward the end. And then as far as other benefits, there's going to be reduction in manpower costs for crews being out in the field and some other reduced maintenance costs. As far as restoring the outage. But again, I'm going to kind of keep things kind of simple as far as the cost numbers I'm using here, but this could actually get pretty complicated to do a full-blown CBA analysis. But in the end, we want to make sure that we've got benefits that would exceed our cost. So this is a little bit wordy right here, but basically what we've got a circuit that's 5 miles long. We've got customers that are distributed shown in this diagram. And I've got this broken down in laterals, and I've got the customers located on lateral A, B, C, and D. And so you can see these are the customer counts, and this is kind of assuming a tapered distribution of load. The further we get from the substation, the less number of customers there are. Feeder automation generally does not help out for faults on the laterals themselves, because that's just going to involve fuses or recloser fuse coordination, whether you're doing fuse savings or not. So what the feeder automation is more focused on is the main feeder. Okay, that's really what feeder automation is going to benefit. And so if I've got, again, faults on these taps, I can maybe do some tree trimming, but the feeder automation is not going to help that too much because I don't have any backfeed points on these laterals. Where in the main feeder I might. So what we're going to start with is we're going to make some assumptions on the failure rates. We're basically going to be assuming in this case that we have, that we've got 0.4 failures per year per line mile with the mean time to repair of 4 hours. We're just going to go ahead and assume all the faults are permanent and that the station breaker can be operated via SCADA. So that means the switching time would be 0 for the station breaker. And again, I'm not going to consider any lateral faults. I'm not going to consider any temporary faults in the backbone. I'm just going to be looking at permanent fault cases. So we'll start off by doing a base case. And then what we're going to do is we're going to look at adding a manual switch at the midpoint. Let's suppose that costs $3,000 to install. Going to see how that's going to change SAIDI and SAIFI. And then I'm going to assume I'm putting in a midpoint recloser that costs $40,000. Now, these types of costs would be the cost of the equipment is purchased from the vendor plus the manpower required to install in the field. So that's sometimes what we refer to as like a loaded cost. Both of those items can be updated in the asset base for the utility. The other thing we'll consider is taking the case C and adding an automated switch at the tie point. This is not a fault breaking switch. It can transfer load only. So this would be a lower cost type of a motorized switch. And then as another option, we're going to rework B, but what we're going to do is we're going to have the combination of the manual switch with a fault current indicator, and we'll assume that the fault current indicator costs $3,000. And what this does, that it reduces the time to switch because we can get the crew there much more quickly. And finally, what we'll do is we'll compare all these different types of options. So here's the base case, and what I'm doing for the base case is I'm going to go ahead and lump customers A and B and C to D together, it'll just kind of simplify my calculations. Essentially, they're equivalent from the standpoint of looking at reliability improvements on the main circuit. So similar to what I did for the reliability calculations earlier this semester, I'm going to put all this stuff into a spreadsheet. And so if I don't have any means of separating faults in the circuit, and if the breaker operation outages everybody, then basically if I have a lambda of 0.4 per year per mile, and if I got 5 miles, I multiply those together, and what I'm going to get is I'm going to get 2 permanent fault events per year on the circuit with mean times the repair of 4. And so this is going to give me a SAIFI of 2 interruptions per year and a SAIDI number of 8, because it takes 4 hours to fix each one. So this is the base case right here, 8 hours per year of outage and 2 interruptions per year. So next thing I do is I put in a manual switch. I just put this at the center point, and this is going to bisect the circuit. And so I'm going to break this into a feeder top and a feeder bottom. And if the lambda is 0.4 per year on each section, I'm going to have 2.5. Well, actually, what I'm going to have in the circuit still is I'm going to have 0.4 times 5. I'm going to have 2 events per year still. The difference in this case is that if I have the fault here and the circuit breaker operates, I can send a crew out there and get the switch open up in an hour. So what's going to happen if I have the fault up here? Well, everybody's out of luck. That's going to be an event that's going to take 4 hours to fix, but for everybody. But if I had the fault down here, then I can get that switch open in an hour, and basically these customers at AB, these 900 customers, they could be restored in 1 hour. The 600 customers are just going to have to wait for 4 hours. So when I plug all this stuff into my spreadsheet, then basically I still have a SAIFI of 2, but now I have a SAIDI that goes from 8 to 6.2. So quite a bit of improvement just for putting on a manual switch, which isn't really that expensive. Now, when I put the recloser out there, what the recloser does is it kind of operates like an automated switch. In other words, when the fault occurs, then this recloser operates. It doesn't even cause the breaker to operate. The recloser just operates right away and isolates all the customers at this location from a fault on the second segment. If the fault occurs up here, everybody's out of luck, all right? So if I got 2 2.5 mile segments, then the fault occurs at the top. I'm going to have 2.5 miles times 0.4, so I'm going to have one of these events per year. It's going to cause a circuit breaker to lock out. I get a fault at AB. I get a fault at CD, 4 hours for each. Then I got my contribution to SAIDI is going to be 4 hours. However, if I have a fault at the bottom point, and this is going to occur on the average of 1 time per year, the circuit breaker doesn't lock out, the recloser locks out. And note that as far as the count at AB, it doesn't see any outage at all right? So both these numbers are 0, but customers at the CD location see 1 outage that takes 4 hours to fix. And so you got 8 outage hours for CD, you got 4 outage hours for AB, and this gives you a net 5.6 hours per year for your SAIDI with a corresponding SAIFI of 1.4 per year. The other thing that kind of goes on here that kind of helps with the recloser benefits is you got more customers above the recloser than below the recloser. So, you know, anytime you're making a change that impacts a large number of customers, that's going to impact your numbers to a greater degree. So anyway, now the difference between having the manual switch and the automated switch, before we were at 6.2, now we're at 5.6. So not a huge difference on the SAIDI side, but it drops the SAIFI down from 2 to 1.4. The next thing I do is I look at putting the automated tie switch in here, because if I have a fault upstream, then at least these customers at C and D could get connected to the alternate source. So this is an event that's going to occur once per year. When that happens, then I'm sorry, so we kind of circled the wrong one in that case. So let me go ahead and fix that. So what's going to happen when I have a fault up here? Basically, what's going to happen? The circuit breaker is going to lock out. What we can do in this case is we can actually have some logic that very, very quickly opens up the recloser, closes in the sectionalizer, and basically what's going to happen is we don't see an event at CD anymore. So what this would mean is we'd have to have some pretty fast logic. It could be centralized, where we have a centralized decision maker communicate to all these devices, so that you could have like a single master. Or another way we can do it is through having some peer-to-peer based scheme where these switches are talking with each other and they're making the decisions through some type of distributed logic. But anyway, what this does is it gets us down to a SAIDI of 4 hours per year with a SAIFI of 1 interruption per year. So kind of a pretty substantial change if we can automate that tie switch as well. All right, so if we're going to put that recloser in there and expect to get more benefits, it would really hope to have an automated tie switch as well in this particular case. So finally, we look at a situation where what I'm going to do is I'm going to put in this manual switch, but something I'm going to do in conjunction with that is I'm going to put in a fault current indicator. And so it's like semi-automation in a way. We're not controlling the switch, but we're getting information that can kind of help us position the crews more effectively. So now what's going to happen in this particular situation, if I have a case where I have a fault in the feeder bottom, what's going to happen is I know when this circuit breaker trips open that I know very, very fast the fault's down here. All right, that's the really advantage of this scheme. So instead of having the crew ride the line from the top of the circuit, I could just send them right to this switch location and they could start from there. So in this case, if you have a fault on the main feeder bottom, then this mean time to switch goes from 1 to 0.333. And if you look at how this propagates through, as far as helping out the customers at the AB location, we can see what that does is it drops down the outage hour time. So you still get 2 interruptions per year, but now you get the SAIDI down to 5.8. And so anyway, you've got all these different cases, and what we could do is we can compare them together, where you have the base case, then you add the manual switch, and that's going to cost you $3,000. You add just the recloser, that'll cost you $40. The recloser plus the automated tie switch costs you $52, and the fault current indicator is $6,000 or $6K. And what you can do is you can start looking at a cost to benefit ratio in terms of dollars per outage hours reduced. So in this case, I'm able to improve SAIDI by 1.8, and it only costs $3,000. And so if you take the ratio of the dollars to the outage hour improvement, this is $1,667. Look at this for adding the recloser. I got an improvement of 2.4. That has a cost to benefit ratio of $16,667 per hour. So quite a bit pricier, factor of 10 times more expensive. Automated tie switch, $52,000. I get a cost to benefit ratio of 13,000. I got fault current indicator out there. What happens is I pay more for having the indicator, but the cost to benefit ratio is going to be about $2,700 per outage hour reduced. So what can you make from this right here? Well, the simplest solution is the one that has the best ratio. All right. What you run into though is, maybe if you just put one switch out there, you get a pretty big benefit. But if you start putting more and more switches out there, what you're going to find is that ratio is not going to be as good for every switch you put out there. In other words, you're going to hit diminishing returns out there. So switches are cheap, but you can only put so many out there and get these improvements, get these large improvements. But anyway, that's the first thing you really ought to be looking at, is just make sure you have all your manual switches in the right locations. So this is really kind of a low-hanging fruit. If you needed to have the fault current indicator out there anyway, I mean, marrying that with the switch would make a lot of sense. So maybe you don't have a fault current indicator every switch, but maybe you use that with switches like in certain key areas where it's hard to do a search. So if you're going cross country with a feeder section, maybe that's a good place to have a fault current indicator. The thing about putting the reclosers out there is we're probably going to need these on certain long circuits anyway. They're used a lot in feeder automation programs where you want to kind of bisect the circuit or break the circuit into 2 or maybe even 3. So you may need that for protection coordination anyway. And then the other thing you would have to look at, which I didn't do here, would be you'd have to look at other alternatives like tree trimming and adding animal guards and things like that. Maybe improve lightning protection is a way for reducing the number of faults per year. So this is the sort of work you go through if you're a distribution planner and you're looking at the impact of feeder automation. And where these numbers would make a lot more sense, obviously, is if we're talking about larger number of customers getting impacted, or you're talking about more critical numbers getting impacted. And so these costs are really kind of high, as you can see for the automation. This is why utilities are not going to really want to automate 100% of their circuits. They really can't cost justify that. To put automation everywhere doesn't make any sense. Maybe to put automation on 5 or 10% of its circuits would make sense if those were like the worst case circuits, or if those are circuits they had either a lot, many, or very, very critical customers like hospitals and police stations and things like that. Now, if you wanted to get customer side costs in the picture, in other words, just if we had the cost of the automation, that doesn't give us the complete picture, right? Because all we're looking at is comparing projects together. In this case, what we're doing is maybe doing a ranking of projects we want to do. But as far as whether we can make the case with respect to customer costs, then what we'd have to do is we'd have to have a way of assigning a dollar value to the customer benefits. And what I've done here is I've gone to this ICE calculator, which I talked about earlier this semester, and I plugged in some numbers, which I think would be typical for North Carolina, where if I had 1,500 residential customers associated with the feeder, and if SAIFI was 2 and SAIDI was equal to 8, then what would be total interruption cost per year? And what they give you in this ICE calculator, and this is based on 2016 data, is that there's a cost associated with this of $15,804 per year. All right. So on an annual basis, this is supposedly what this level of reliability is going to cost this number of customers. And that might be the total number of customers, say, like on a feeder, right? So now what you'd have to take a look at would be, if I look at that Recloser plus automated switch option, which is going to cost me $52,000. Let's suppose that project lasted me for 10 years, and let's just neglect the cost of maintenance. Okay, so if the customer value is $15,804 per year, well, what's the present value of that particular benefit? And what you can do is you could start to apply things like inflation rates and the cost of the utility to borrow money. And here, you'd say they had to borrow that money for $52,000. Then what you're going to see in this particular case is that benefit over a 10-year period would be $63,000. So then what you could start to be looking at in this particular case would be, okay, does spending this amount of money give you know enough benefit where it would have this sort of value to these particular customers, right? So anyway, this is the sort of thought process you would have to go through. Is you would have to basically look at all the different projects. You would have to figure out what things are going to cost. You're going to have to know what the lifetime of the project is. And then what you'd be looking at is you'd be looking at 10 years of reliability benefits and start to look at whether this makes any sense or not. Now, remember that this case right here, when I talk about the SAIFI of 2 and the SAIDI equal to 8, well, this is going to cost $15,804 per year. What I'm doing with this project, I'm just dropping this in half, right? So this is really going to drop this down to more like 7,000 per year. And what that's going to do, that's going to drop this benefit down to maybe like $31,000 per year. So I have a situation where the cost is more than the benefit as far as the reduction in the SAIDI and in the SAIDI index. But then if there's some other things you're going to need the recloser for, then maybe it's still cost justified, or maybe there's some other political reason to do it because you have a hospital or some other public infrastructure involved that you want to have a higher value reliability for. So anyway, just some basic information here on feeder automation. And if you want an additional reference on this, this is kind of an older book by now, but there's a book by James Northcutt Green and Wilson, I think it's Bob Wilson, on control and automation of electric power distribution systems. And there's not too many books out there on feeder automation. Unfortunately, it's not available as an ebook. But Northcutt Green worked for ABB a long time working in the automation space. And there's actually a lot of good stuff in this book on doing reliability calculations like we talked about before, and the different things that are associated with doing automation in the field. So if this is of interest to you, this would be a book available in the NC State Library. You'd actually have to get the paper copy of it unless you bought the book. But it's actually one of the few books out there that has anything on hardware at all. So what we'll do in the next lecture is we're going to take a look at volt VAR control. This is another type of a popular smart grid type of application, probably more popular than FLISR actually. But we'll take a look at volt VAR control and see how we can actually come up with some logic for switching the capacitors and controlling the regulators for improving the performance of our utility automation.